And now I would like to introduce you to today's presenters. Our first presenter is Ken Schweitz. Ken is president of Premold Corp. As an engineer, he has over 30 years experience in product design and development. For over 20 of these years, he has been focused on plastic parts. And after working with vacuum forming, pressure forming, and injection molding, he has spent the last 15 years specializing in rim. Ken is very active in the rim industry, and he has published technical articles, presented at industry-related conferences, and written numerous rim design guides. He maintains contact with other molders and various suppliers working to advance the science of rim molding. And also joining us today is Doug Culbertson. Doug is Vice President of Business Development, and he's been with Premold Corp since 2005 and has over 30 years experience in plastics molding. Doug is very active in the life sciences industry, and regularly presents technical seminars and attends industry conferences. He is a member of SPE and ASLMS. And without any further delay, I would like to hand it over to our first presenter, Doug Culbertson. Doug, you now have the floor.
Well, thanks for the introduction, Melanie, and good afternoon to our webinar attendees. The rim process has numerous advantages, and I'll discuss 4 of them here. Advantages include good return for low-quantity parts, low-cost molds, short tooling lead times, and much greater design freedom. The picture on this slide illustrates enclosures and housings molded for the life sciences industry. Reaction injection molding is well suited for medium and large-sized enclosures in low quantities, and rim resins are formulated to provide good part stiffness and impact resistance for these applications. Rim is economical for low-quantity molding because tooling setup and run costs are lower. Molding temperatures and pressures in the rim process are much lower than high-pressure injection molding. Maximum mold temperatures of 180 degrees Fahrenheit and process temperatures of 50 psi are typical. As a result, production setup times are shorter, and rim parts, like those pictures here on this slide, are produced in small batches that minimize customer inventory costs. Production batches of 25 or 50 parts are quite common. This is particularly advantageous for manufacturers in the life sciences industry needing large enclosures and housings for their instrumentation. Another advantage of the rim process is low-cost production tooling. Because reaction injection molding is a low-pressure, low-temperature process, the production tooling is made from basic-grade aluminum. Therefore, the tooling material is much less expensive and machining time is faster. In addition, side actions are less expensive because rim molds use low-cost air cylinders or hand-loaded loose pieces to achieve complex features. The 3 pictures on the bottom of this slide illustrate the core, cavity, and ejector system of a conventional rim production mold. Often, molds can be designed without ejector systems for additional cost savings. A third advantage of the rim process is short tooling lead times. Because rim production tools are made of basic aluminum materials, the CNC machining process is faster. Therefore, designers can meet aggressive project schedules. This results in new projects being brought to market more quickly. Additionally, expensive and time-consuming EDM machining is unnecessary. Using robotic CNC systems and machining directly from 3D CAD models ensures that the tooling and finished parts will be precise. Also, changes or revisions to production aluminum molds can be completed quickly and cost-effectively. And a particularly important advantage of the rim process is greater design freedom. Parts can easily be designed with variable wall thicknesses, tall bosses, minimal surface draft, and other complex features with less rigid ratio restrictions. Often, multiple parts can be integrated into a single part, resulting in improved cosmetics, lower tooling costs, lower part costs, and even lower assembly costs for the instrument manufacturer. High-pressure injection molding and pressure-forming processes simply do not allow these freedoms. The picture on this slide illustrates a large part with variable wall thicknesses and tall bosses. In the next section, Ken will describe how the rim process works.
Thank you, Doug. Some people are not familiar with the rim process. Well, let's take a look at how the process works. This schematic summarizes how rim molding machines and the rim process works. Two different liquids, isocyanate and a polyol, are held in separate feed tanks or day tanks that we see here and here. Other portions of the separate circuits regulate the temperature and pressure and specific gravities of the two liquids. And we see the supply line and the return line here and here. Separate pumps for the iso and the poly that we see shown here and here regulate the pressures, flow rates, mix ratios, and feed rates of the two liquids. A control valve called a mix head is typically attached to the mold. The job of this valve is to divert the two liquids from their return lines or recirculation lines, divert it from the supply line into a mixing chamber in the mix head, and then flowing out into the mold. As I mentioned, the two liquids are first mixed in the mixing chamber of the mix head, and as they do their impingement mixing there, flow out into the mold and fill the mold. Now, normally the mold is closed during the injection portion of the cycle, but it's shown open in this schematic here so you can see more of the components. The injection portion of a molding cycle in rim normally lasts from 1 to 5 seconds, depending on the size of the part and the material that you're processing. Now, most rim materials or resins react and change from the liquid to the solid within about 5 or 45 seconds after they're first mixed in the mixing chamber or the mix head. Again, that depends on which material you're using for your application. This is a typical rim dispensing unit or molding machine. You'll notice the closed loop computer controls over here to, again, regulate the pressures and temperatures, flow rates, mix ratios, and specific gravities of the two liquids. Rim resins are normally sold as two-component systems by manufacturers like Bayer and Dow, to name a couple. And here we see in the background in this photo day tanks or feed tanks here for the isocyanate and the polyol. And then the rest of the machine is plumbing, heating, and cooling components here, and the pumps to regulate the flow of the resins, the two liquids, into the mixing chamber or the mix head. Now, as soon as the two liquids of the resin system are mixed, a chemical reaction starts between the two liquids and creates a thermoset plastic part. That's really at the heart of the rim process and the nature of the rim system. As we mentioned, that this chemical reaction might take anywhere from 5 seconds to 45 seconds depending on which resin you're using. And the typical molding cycle for rim might be between 1 to 5 minutes depending on part size, wall thickness, the type of mold that you're running, that sort of thing. Rim materials or resins are also available in a wide variety of material properties, so you can tailor those to your needs. but it's because of this chemical reaction that the two liquids create the thermoset solid plastic part. Now, less than 50 psi of pressure is created during the molding cycle for the rim process. The rim process is based on resin flow to fill the mold instead of a high pressure to force the resin into the mold. Now, because of the importance of resin flow to fill the mold, rim presses typically tilt and rotate, as we see in this picture here, to orient the molds at a compound angle during the injection of the resin. Now, you see an aluminum mold clamped in this particular press here, oriented at the compound angle. What you can't see very well in this photo, because we wanted to get an overall picture, is the mix head that's attached at the lowest point or the bottom of the mold as it's oriented at this compound angle to inject the resin. The mix head's attached to the lowest point or the bottom of the mold, so the liquid resin is injected into the mold at the bottom, and then the resin can flow through rather rapidly to fill the mold. Usually it fills within, a typical time would be 2 seconds. Again, you've got between 1 and 5 seconds depending on the resin system you're using. But it flows through and fills the mold quite rapidly. Now, air vents are placed at the top end of the mold here as it's oriented at its compound angle. And as resin fills the mold from the bottom, the air escapes out the top end of the mold through those vents. The computer controls on the dispensing unit that we looked at previously, they stop the injection of the resin when the mold is full. The rim molding process, even though the resin injection happens fast, the process requires less energy and results in less internal stress in the parts. And that's because of the low pressure and the low temperature and the chemical reaction to form the solid plastic part. So unlike high pressure injection molding, with the rim process, you're flowing liquids into the mold at low pressure, low temperature, chemical reaction to turn them into a solid plastic part. Whereas high pressure injection molding with thermoplastics, you're taking a solid, melting it, packing it into a mold under high pressure, and letting it freeze, usually in a stressed condition. So consequently with rim, you can mold some large parts or long and thin parts without a lot of hidden stress or without any hidden stress in some cases. So it makes the rim parts very resistant to warpage and so on. Typical temperatures that you see in the rim process are mold temperatures of about 180 degrees Fahrenheit. Resin temperatures in the dispensing unit are about 100 degrees Fahrenheit. But when the chemical reaction is underway to form the solid thermoplastic or thermoset plastic part, the chemical reaction gives off an exothermic heat which might peak at about 250 degrees Fahrenheit for a brief period of time. So next, Doug is going to go through some of the part design advantages you get with the rim process.
Thank you, Ken. As we've discussed, reaction injection molding is a design-generous process with far more design freedom than high-pressure injection molding or pressure forming. This is because rim parts are much more resistant to sink and warp. Therefore, details like large ribs, tall bosses, variable wall thicknesses, undercuts, and even complex contours are much easier to achieve. Also, having custom features like undercuts and side action are less expensive in rim production tooling. These factors make it faster and easier to design rim parts. The design guide for rim, pictured here on this slide, is available as a hard copy or electronically and was written specifically for industrial designers and engineers working in the life sciences industry. Reaction injection molding is more forgiving of variable wall thicknesses within the same part. This allows part designers and engineers to easily incorporate assembly features like tongue and groove joints, alignment shifts, and reveal gaps. Designers can also tailor the desired thickness and stiffness of parts in specific areas while minimizing part weight and cost. The inherent resistance of rim parts to sink and warp allows part designers to incorporate large diameter bosses and tall ribs without worrying about sink marks or warpage. In reaction injection molding, side actions and undercuts are less costly because these features can be achieved with hand-loaded loose pieces and inserts. Therefore, expensive hydraulic side action systems are unnecessary. The picture on this slide illustrates that it's easy to design low-cost hand-loaded loose pieces. Molds for large rim enclosures and housings used in the life sciences industry often have multiple hand-loaded loose pieces designed to achieve important cosmetic and functional features in the parts. It's easy to mold complex features and fine details on both sides of rim parts. The low viscosity and easy mold filling capability of rim resins makes this possible. Designers and engineers are encouraged to design in all the features they want because even complex features don't need to be glued on or machined in after the parts are molded. All of the cosmetic and structural features of the large U-shaped part pictured on this slide are molded in, thereby eliminating costly secondary operations. Additionally, some rim parts, like this hood, are produced in two versions from the same mold using interchangeable loose pieces. This design freedom can significantly reduce your production tooling costs. And with the rim process, multiple parts can easily be integrated into one part. This is particularly important for the life sciences industry, where large enclosures with complex geometries are common. The picture on this slide illustrates a large cover that was originally designed as 4 separate parts, 2 sides, a top panel, and a front panel. During an early design review, it was determined that all 4 parts could be molded as the single part you see pictured here on this slide. This reduced the number of molds and parts from 4 to 1, which significantly reduced the client's overall tooling and part costs. This one-part design also resulted in faster system assembly time for the customer when they went into production. Added benefits of the rim process are thermal and acoustic insulation properties, especially when designing thicker wall parts. Also, the inherent stiffness of rim resins means support ribs in rim parts are usually unnecessary. This saves instrument designers and engineers space for their internal components. These design advantages allow project teams to achieve highly stylized and complex geometries with all the features molded in. Ken will now continue with some additional part design advantages of the rim process.
Thanks, Doug. Because parts from the rim process are so resistant to sink and warp, it's easier to mold in locating features into your parts. Here we've circled some ribs and tabs molded on the inside of a part here that form an interlocking feature with a tongue that's molded in the mating part. Features like this help you fit your assemblies together easier in production, and it makes them far better or more consistent in the field. It makes them fit far better in the field on a consistent basis after your machines have been serviced. So other interlocking tabs, tongue and groove joints, overlap joints, bosses, and mating into rings and holes, a lot of different features like that can be molded into rim parts. Because of the low viscosity liquids used in the rim process for the rim resins, these resins flow easier to fill large, complex molds. For example, you can gate at the bottom of this part here that's 65 inches long, vent out the opposite end here and flow around an open window that's cored in the part without any problems. So as part designers, you don't have to worry about filling out large, complex parts. You can use the tall bosses, thick ribs, and thin sections, and a lot of other features that we've mentioned, all in the same part without molding problems. Now, depending on the rim resin that you choose, that resin might make a rim molded part stiffer than its counterpart in high-pressure injection molding. Because a lot of the rim resins are very rigid, it eliminates the need for a lot of reinforcing ribs on the inside of a part. So that keeps your part cost and your tool cost down. You can also get foamed resins in the rim process, and these leave you with a solid inner and outer skin on the part and a slight foaming action in between those inner and outer walls, and that allows you to really keep the stiffness up while keeping the part weight and the part cost down. You can get tight dimensional tolerances with a rim process, fairly easy to achieve because you're dealing with a closed mold that control all the features of a part. So unlike the process for thermoplastics, rim does not, as we mentioned before, does not melt a solid and then overstress it into a mold and then let it freeze in that stressed condition. You're dealing with low pressure and low temperature flow, chemical reaction to form the solid plastic part, relatively stress-free. Rim parts normally have tolerances of thousandths of an inch per inch are pretty typical. The tolerances are normally stated in an inch per inch basis because it's not unusual to be dealing with large parts with the rim process. Now, in the life sciences industry, it's important to have a UL flame rating. Usually UL 94V0 is required. There's a lot of rim materials or resins, both solid or foamed, that give you this UL 94V0 rating. And you can achieve this at some pretty thin wall thicknesses, maybe as low as 1/8 of an inch wall thickness. Rim resins are also very resistant to attack by chemicals because they're thermoset resins formed by a chemical reaction. That's especially beneficial for people in the life sciences industry because they're typically having their parts and their machines exposed to cleaning chemicals and whatnot. The low molding pressures and temperatures in the rim process make insert molding and encapsulation easier to do. Now, in general, if your parts that you want to encapsulate or insert mold will withstand 50 psi and about 250 degrees Fahrenheit for a brief period of time, and those parts won't be ruined by contact with liquids, because remember the resin is flowing in as a liquid, chemical reaction turns it into a solid. If your inserts will withstand that, you can insert mold it with the rim process. You do have to consider the size and stiffness of the insert because the resin wants to shrink a little bit, the insert doesn't want to shrink. But again, a rim molding engineer can help you with those considerations. Some of the benefits of insert molding or encapsulating parts are you hermetically seal the parts that you insert mold or encapsulate, protect them from the environment. You can save a lot of assembly labor instead of putting all the components together after molding. And also the resulted molding parts give you a tamper-proof and safer product or safer assembly than you would have if it were assembled after molding. That covers some of the highlights of the part design advantages the rim process offers. Now Doug's going to tell us about the high value that rim molds offer to you.
Thanks, Ken. I speak to project teams across the country, and they're always surprised by the value they can get from rim production molds. Because reaction injection molding is a low-pressure, low-temperature process, production molds can be made from basic-grade aluminum materials. This lowers your tooling costs and minimizes your tooling lead times. Therefore, product development time is reduced and speed to market is optimized. And of particular importance to designers and engineers working in the life sciences industry, these basic aluminum production tools provide many years of production life and thousands of production parts without losing tight part tolerances. And as the picture on this slide illustrates, rim molds use simpler ejector systems, which also helps keep tooling costs lower. This is because rim parts require less draft than similar parts designed for high-pressure injection molding. The reaction injection molding process allows toolmakers to utilize low-cost side actions like air cylinders and hand-loaded loose pieces to achieve complex geometries. This gives part designers and engineers tremendous design freedom because they don't have to worry about driving up tool costs and lead times when they add a feature. The picture on the left side illustrates a low-cost loose piece that illustrates a touchscreen window in the finished part, and the picture on the right side shows a simple air cylinder system operating a side core. Additionally, part designers and engineers save time and minimize costs because they don't have to worry about coring out for thick areas or addressing hot spots in the molds. Aluminum production tools for reaction injection molded parts are more cost effective because water lines and cooling systems are simply less critical. The low temperatures characteristic of the rim process make this possible. Lastly, multi-cavity family molds can be used in the rim process. It's relatively easy to balance the cavities on each side of the mold for uniform resin fill. The low viscosity of rim resins ensures complete fill in all the cavities. The use of multi-cavity molds reduces overall tooling costs. In many cases, multi-cavity molds can even be designed for large parts. An added benefit is multi-cavity molds are designed with mechanical shutoffs, so each cavity can be run individually if necessary. That covers some of the reasons rim molds are low cost and high value. Next, Ken will outline some of the post-molding options you have with rim production parts.
Thanks, Doug. That's another benefit of the rim process. You have a wide range of post-molding options to choose from. In the life sciences industry, it's very common to require EMI RFI shielding to protect either the internal electronic components or sensitive electronic equipment outside the unit that you're building. A shielding layer can easily be sprayed on these complex surfaces of the part on the inside, and that's sprayed on in a liquid paint form so that you can easily cover the contours, nooks and crannies. Rim molded parts can be painted various cosmetic colors as well, and also different textures. Multicolors and metallic colors are often done. Like all painted materials, surface preparation is the key to getting good, durable coatings on a rim part. Rim parts can also be decorated using the silk screening or pad printing process. If threaded inserts are desired for your application, you can use a self-tapping style of insert shown here, put in by either an air or electric-powered driver. Usually the hole is molded in the plastic part here, so it's molded to the correct size, and then the insert is put in just like a self-tapping screw, but it's a one-time installation. So having that threaded insert in there, you can run your screw in and out as many times as you want to assemble and disassemble the product. You can also use self-tapping screws with rim, and you can reuse those 5 or 6 times just like you would with any other plastic part. Rim molded parts for the life sciences industry are often painted after molding. This is because the cosmetic requirements for the OEM's product is quite high for the covers and housings that represent their final product. So it's not unusual to do a complete removal of the gate and vent vestige from a rim part before it's painted. As designers, this gives you an extremely high amount of flexibility to achieve really some unmatched aesthetic effects on your final product. This part was originally designed as 2 pieces to be glued together, and there was going to be a seam right down the center line of the part here. Now, because rim allows thicker wall sections and varying wall thicknesses within the same part, which you see a nominal wall here, and you can kind of see a thicker wall here and here, even though you can't see the inside of the part. That's the way it was molded. This part could be molded as one piece with the rim process because it is forgiving of those varying wall thicknesses. So consequently, the part cost and the tooling cost were less molding it as one piece in the rim process. Also eliminated the joint that would have run down a very cosmetic area of the part, and it made the part stiffer and more structural, molding it as one piece instead of two pieces fastened together. So as you can see, parting lines, gates, and vents, all of those can be completely removed from a rim part before the painting is done, and really gives you, as we see here, some outstanding cosmetic or aesthetic effects in the final product. You can also easily machine rim parts after molding. Normally it's more economical to mold the part to its final shape than to machine it, but machining can be a good option for special versions of parts or low volume options that you may need to produce. We've covered a lot of key points about the rim process in a short period of time. Doug, why don't you summarize those for us?
Okay, I'll do that. RIM is economical for low-quantity injection molding because setup costs are low. This is because reaction injection molding is a low-pressure, low-temperature process. Therefore, RIM is well-suited for medium and large enclosures with complex geometry and high cosmetics. This is especially important for low-quantity housings used on medical devices and lab instruments. Secondly, production molds cost less for more features. Reaction injection molding offers high-value molds because designers get more features at lower cost. Inexpensive side actions and hand-loaded loose pieces allow designers to achieve complex geometries at low cost. This means you can incorporate more features into each part and combine parts for greater efficiencies. Project teams receive high value from each rim mold. Third, tooling lead times are shorter. Rim tooling lead times are shorter because basic-grade aluminum molds are machined faster. This reduces tooling costs and optimizes speed to market. Lastly, RIM provides more design freedom due to its low molding pressures and temperatures. Since RIM is a low-pressure, low-temperature process, designers save time and money because they don't have to struggle finding ways to core out difficult geometries or avoid thick walls, tall bosses, or undercuts. All these features are easy to design using the RIM process. This concludes the presentation portion of our webinar. Thank you for attending. And now, we'll turn it over to Melanie and take your questions.
Thank you very much, Doug. Thank you, Ken. So we do have questions in queue. Why is there no vent or gate vestige? Why is there no vent or gate vestige?
Okay, the reason there is no gate and vent vestige, let me clarify that there is on the molded part when you first take it out of the mold, but these are removed. The gate and vent vestige are removed before the part is painted. So typically you would want that removed even if you weren't going to paint the part, but it is present during the molding of the part.
Okay. What type of reduced draft can be used with RIM? What type of reduced draft can be used with RIM?
With the RIM process, you can use less draft and a very low amount of draft on the part that you design. It's not unusual to use 1 degree or even as low as a 1/4 degree. In some cases, if you need side action on the part anyway by air-powered core or a hand-loaded loose pieces, you can even go down to 0 draft because you have the side action anyway. But 1/4 degrees of draft is very achievable.
Thank you. What is the typical tool life of a RIM mold? What is a typical tool life of a RIM mold?
Tool life of production rim molds are designed for the project specifics. Some projects necessitate a tool that's going to produce 100 parts a year for 10 years. So we might expect the life expectancy to be 1,000 or 1,500 cycles on that tool. Other projects, clients want 1,000 parts a year for 10 years. Therefore, we're designing and building a tool that will give us a minimum of 10,000 cycles or maybe as high as 15,000 cycles. Many of the production tools that we produce achieve much higher life expectancies. 20, 30, 40,000 cycles is fairly common.
Thank you. What is the typical lead time for an average size rim mold? What is the typical lead time for an average size rim mold?
Well, there is no average size rim mold. They're tremendously variable. Some parts are as small as 6 inches by 12 inches for a thin bezel, for example. Other parts are as large as 6 foot by 3 foot by 2 foot. And the size, the general size of the part is going to determine general lead times. Small parts might take 7 to 8 weeks to be completed, and then a few more days for the first article. The largest parts, the 5 foot or 6 foot parts by 2 foot, probably are going to be 10, 11, or maybe 12 weeks, depending on the geometric complexity.
What is the average size part for the rim process? What is the average size part for the rim process?
The average size part for the rim process for pre-mold is about 2 foot by 3 foot, even though we make parts as small as 6 inches by 10 inches and parts as large as 5.5 feet by 3 feet. Our average or our median size part is probably about 2 by 3.
Okay. How thick or thin can the part walls be within a rim part? How thick or thin can the part walls be with? I'm sorry. Let me just repeat that. How thick or thin can the part walls be within a rim part?
Okay. The question is how thick or thin the walls of a part can be, and the liquid resins as they flow into the mold are very low viscosity, so depending on how far it has to flow, you can get down into 10, 20 thousandths of an inch thickness. There are some rim resins that have a foaming action that will allow you to mold them wall thicknesses as thick as 2 inches for that thermal and acoustic insulation that Doug was describing earlier. Normal wall thicknesses are about 1/8 of an inch to 3/16 of an inch because in the life sciences industry, almost everybody needs a UL 94 V0 flammability rating and also a certain amount of structural integrity, but you can go much thicker and thinner.
Thank you. Can steel or aluminum components be molded into rim parts? Can steel or aluminum components be molded into rim parts?
Yes, as far as insert molding or encapsulating parts within rim, the question is, can you use steel or aluminum? You certainly can. You could even use wood, glass, printed circuit boards, wire components, thermostats, a lot of different things, as long as it won't be ruined by contact with the liquid resin as it flows in. In other words, you wouldn't want something that fills up with liquid and turns into a solid plastic from the chemical reaction and then no longer functions. Also, it needs to withstand about 50 psi maximum and a temporary heat of about 250 degrees Fahrenheit, but you could even insert mold glass under the right conditions.
Can different size geometry parts be molded in the same family mold to save cost?
Generally speaking, to do a family mold or a multi-cavity mold, the geometries have to be quite similar. A part that's 6 inches by 10 inches can be run perhaps with a part that's 7 inches by 12 inches, contingent on the complexity of those geometries. However, it would be quite difficult to combine a 6-inch by 10-inch part and a 2 foot by 3 foot part in the same multifamily tool.
Okay. Why does the mold need to be tilted or rotated for venting of air? Why does the mold need to be tilted and rotated for venting of air?
You want to tilt and rotate the mold to a compound angle when you inject the resin, because the resin is entering as a flow process. You're not pressurizing the mold cavity to force all the air out and force the resin in. The way to visualize the rim molding process while the resin is going in is like filling a vessel with water, and really at very low or almost no pressure. So you really want to tilt and rotate that mold depending on the part geometry, so that as that liquid resin enters the bottom of the mold, the air can rise out the high points to the top of the mold, and that's really at the heart of why you need to tilt and rotate the molds to a compound angle, which is dependent on part geometry and the mold design. Is you're using very little, if any, pressure to force that liquid into the mold. So if you've got a blind corner that the air cannot escape, it's going to be trapped. In high-pressure injection molding, if you trap air, you can tend to force it out with the high pressures, but you could also get a burn mark. With rim, you don't have those high pressures. It's dependent on flow and venting the air ahead of that flow.
Thank you. What are the typical low volume quantities that are advantageous for rim?
Well, in particular for the life sciences industry, the types of projects we see here have low quantities in the range of perhaps 100 EAU up to maybe a couple thousand EAU estimated annual usage. There's considerable variation there. Many of the projects are in the 200, 300, 400 range, but typically the largest volumes we would run is maybe 2 or 2,500 parts per year, again in smaller batches, 50 or 100 parts at a time.
How do you ensure complete mixing of resins?
To ensure the complete mixing of the isocyanate and the polyol components of rim resins, you've got the mix head design, which is dependent on impingement mixing of the two streams, the iso liquid and the polyol liquid, those impinging on each other, mixing within that mixing chamber of the mix head. And then depending on the resin system that you're buying, again, either from Bayer or Dow or another manufacturer, they might recommend a detail called an after mixer in the runner system before the resin flows into the mold, into the part cavity of the mold. So depending on if the resin manufacturer feels it needs something additional to ensure mixing, we machine an after mixer into the mold.
Is there material shrinkage with rims?
Yes, there is material shrinkage with rim resins. How much depends on which resin you're using, but that's a science, not an art. Just like any other injection molding process, each resin has a specific shrink rate associated with it, with its processing parameters, and that's very easy to factor into the mold design.
Are rim materials similar to materials used with rubber molds?
A question about whether rim materials are similar to the rubber materials used in molds for rubber processing. I guess that would be highly variable. There are thermoplastic rubbers and there are urethanes that follow the iso and poly chemical reaction rim process to form flexible plastic parts as well, but there's not a lot of similarity there. That basically the rim molds would have some similarity to rubber molds. It would just depend mainly on the life of the mold and things of that nature.
What are the thermo-temperature ranges for rim materials? What are the thermo-temperature ranges for rim materials?
The thermal temperature ranges for rim materials, they might be asking about the heat deflection temperatures or the temperature ranges that you can use or apply rim molded parts to, and that's a very broad range. Typically, you can use rim molded parts in applications as low as minus 50 degrees Fahrenheit, and then depending on the heat deflection temperature, which again is going to also depend on the loading of your part in its application, you might be able to go up very close to its heat deflection temperature, which could be 250 degrees Fahrenheit or higher depending on which resin you choose.
Okay. Can EMI be applied to rim materials? Can EMI be applied to rim materials?
Yes. Quite commonly, EMI is applied to rim materials. It's particularly typical in on the enclosures and housings that we mold for the life sciences industry, because commonly RF shielding is a requirement.
Thank you. Can thread forming screws be used with rim? Can thread forming screws be used with rim?
Thread forming screws can be used with rim, but the recommendation is to use thread cutting style of screws. As it is with a lot of plastics, again, it depends on the rim material that you're using. In the life sciences industry, a lot of times we're dealing with rigid and solid rim materials, which work better with a thread cutting screw because the resin is much stiffer and doesn't stretch much at all. On a softer, more flexible material, you could probably get away easier with a thread forming screw.
What type of part joints should be used with rim for matting surfaces?
For mating surfaces of rim parts, it's really best to look at the goals of that particular design and some of the limitations that they might have for space and other parameters, how they're going to service the machine and so on. Naturally, the larger the covers, the larger the parts that you're molding that fit together, the more you like to have a tongue and groove or a partial tongue and groove type joint to really locate those large parts very well relatively to each other. But there are a lot of different techniques that you can use to locate two parts together, whether it's a boss that fits with a hole or an annular ring, or it's a tab in a slot. But there again, rim part designer or a rim tooling engineer, we could help you with that.
Can texture be applied to rim parts?
Yes, texture is applied to rim parts typically. In the painting process, the final step of painting, the texture goes on. Customers can select a wide variety of textures. Typically, they will utilize a mold texture booklet and select something perhaps between an 11020 up to an MT 11080.
And Doug, recall the project that we did on a part that was not painted. The mold was textured, so the molded part had color and texture in it, but those are fairly unique applications. But you can texture a rim mold and replicate that texture in the part.
And one other note, increasingly we have clients who are asking for untextured, high-gloss, metallic finish parts. There seems to be a trend in life sciences right now to achieve those types of cosmetics.
Thank you. Looks like we have time to answer just two more questions. The first question is, can adhesive bonding be done with rim materials? Can adhesive bonding be done with rim materials?
Yes, with rim materials you can certainly do adhesive bonding. Again, you just want to choose either a flexible adhesive or a rigid adhesive depending on the application. We can help you with the proper design of leaving room for the adhesive so it doesn't all get squeezed out during assembly or squeezed onto a cosmetic surface. But it's very easy to find an adhesive that works with a rim molded part.
Okay. Are burn marks or knit lines seen with rim molding?
Burn marks are not seen with rim molded parts because you're not generating the pressures that would cause combustion of trapped air, and also you're not dealing with temperatures that would, elevate or boost the temperature of that air, making it easier to combust. Knit lines are fairly easy to avoid with rim parts. To take an extreme example, if you didn't fill the mold in time and the chemical reaction had progressed to where now they're no longer liquids flow fronts meeting, but almost a semi-solid flow front meeting, you could have a knit line. But as we saw an example earlier, and we have numerous large parts that we mold, it's relatively easy to avoid any concerns about knit lines with rim parts.
Great. Thank you very much, ladies and gentlemen, for your attention today. I hope you found this last hour valuable. Before we go ahead and close, I'd like to hand it over to Ken or Doug if you want to leave us with a few words before we close.
Thanks so much, Melanie. The rim process provides an excellent solution for low-quantity injection molded parts. A hard copy of our design guide for rim can be mailed to your attention, and product profiles are available electronically. Thank you for attending our webinar, and please contact Premold Corp with any questions.
Thank you so much for joining us. We hope that we see you at a future event, and you may now disconnect from this meeting.